Hello community, we have a beautiful new methodology for agentic flow. And I got a comment here and I said, hey, in your last video you showed some emotions, please restrict from this. Just give us the pure facts, the documentation and the code, and this is all we need. So, okay, can do this. Here, new study, new code, this is it, thank you. Now, for the rest of us who still have a beating heart, what are agentic workflows? Because honestly, if I look at this, I understand absolutely nothing, not one word. So I have to start all over again. So here we go. Now, the authors tell us for them the definition of an agentic workflow is those LLMs that we use are solving complex tasks by following agentic workflows, which are sequences of operation or steps they call nodes, and you say, aha, that the model executes to complete a task. These workflows can involve multiple stages such as reasoning, generating intermediate outputs, revising some answers and more. And we got a feeling that, okay, structured sequences of LLM invocations accompanied by detailed instruction. And now, if we have those agentic workflows, we code it, no? We put it here in prompt engineering, we define here, if you work with LangGraph, we define here the sequence of our operation, no? And they say, yeah, it requires significant human effort, which limits here the scalability and the adaptability of LLMs to new complex domains. And you say, okay, beautiful. And now the authors have an interesting view, but let's follow their idea. They say, hey, we have two distinct paradigms of LLM applications. We have the agentic workflow and we have autonomous agent. And they argue that these are separated entities, which you could say, really, are you sure? But never mind, let's go with their idea. And they say an agentic workflow completes here the tasks given here statically. So through predefined processes with multiple LLM invocations. We built this as humans, no? However, autonomous agents, the author argue, solves problems dynamically through flexible autonomous decision-making. And now the idea is that they have is here, hey, can we bring a little bit of this autonomous thing here over to the workflow generation? And they go on and say, recent works aim to automate now this design of the agentic workflows, and they categorize this now in three types: automated prompt optimization, hyperparameter optimization, and automated workflow optimization. So let's have a look at the first one, the prompt optimization. You know this, and I've given you the reference study that I would recommend. So automated prompt optimization uses LLMs to optimize the prompt structure within fixed workflows. And I would say beautiful here by Stanford University. This is the study, October 2023, DSPy. For the hyperparameter optimization, which focuses here on optimizing some predefined parameters within the complete dynamic system, I would go here with Stanford University and University of Washington, October 4th, 2024, Archon, an architecture search framework for inference time techniques. And the authors argue now, those two methodologies, while these approaches improve the performance, they are limited in generalizing to new tasks and often require moderate human efforts for task-specific designs. And they sound now, we want to generate an automated workflow optimization methodology, which aims to optimize entire workflow structures, offering more potential for fully automated workflow AI agent generation. But there are already different methodologies available. So let's have a look at one of them that I like, for example. And we have here from mid of August 2024, automated design of agentic systems. And they utilize here code structures to represent workflows and stores here the historical workflow here in simply a linear list structure. Now the authors tell us here that they know this study, but constrained by the efficiency of its search algorithm as it relies on overly simplistic representation of the experience in the search process. So the authors are not satisfied because this is, hey, already from August 2024, so we have to have something better. But if you want to get an idea, please read this particular publication here from mid-August, because they really explain here how you utilize code structure for agentic workflows. And then here we have now their brand new study from yesterday, October 14, and they say AFLOW, automating agentic workflow generation. We have here Deep Wisdom, Hong Kong University, Renmin University of China, Nanjing University, Fudan University, my goodness, and everything else. So what they do now, code will be available at Meta GPT. Nothing to do with the company Meta, by the way. So they say AFLOW now also uses code to represent here our workflows, but goes further by providing now a more fundamental structure. And this is what they call a node. And now careful, this is not the node from your graph structure. I'll give you a definition of the node in a minute. And they say now this structure encompasses various LLM invocation parameters, allowing for more detailed workflow representation. So we'll make another step in the evolution of autonomous automatic agent workflow generation. And here I give you the code. This is the basic structure of a node according to this new study. So class action node, beautiful. So we have the context, the LLM, the schema, raw, JSON, Markdown, XML, and this is already it. Isn't that simple? However, let's look at the complete workflow representation. We have node and edges, and yes, you guessed it, we're going to use here a tree search algorithm. The node. Each node represents here an LLM invocation with parameters. Those parameters, as I just showed you, are the model, so the specific large language model that we will use, the specific prompt structure, the specific temperature to control here the randomness in the output, and the output format. Maybe we go with JSON. And then we have edges. Now, edges, those are a little bit more interesting topics here. Now, represent here the connection and the sequence between our nodes. But our nodes are a little bit different now to what you know from graph theory. And the idea is now edges can be constructed either as graphs or as neural networks, or, as I just showed you here in the publication, as code structures. And this allows here for complex workflows with a conditional logic and loop structures, which we need for causal auguring if we want to improve our logic here. Now, I want to give you here the reference literature, in my view, that I like, that I would recommend to you. If you want to learn here about edges can represent various structures, such as a graph, I would go here with August 2024 here, GPT Swarm, language agents as optimizable graph structures. Highly recommend these studies, and they give you here a flexible structure representing hierarchical, sequential, or parallel relations between nodes, allowing here for complex branching workflows. If we go with the second option, that edges can be represented as various structures such as a neural network structure, I would go here with October 2023. Yes, I know it's an old one from Stanford University and Georgia Tech, but it's excellent. Have a look at this dynamic LLM agent networks and LLM agent collaboration framework with agent team optimization. Imagine more than a year ago they did this here dynamic LLM agent network with code generation in a neural network structure. And this structure can represent complex, non-linear relationship between our nodes, allowing for adaptive and learnable workflows based on input and feedback. Now, as I showed you in this third category here, edges can be represented as the structure of a code structure. We already have from August of 24 here, automated design of agentic system. And now the beauty of this idea is, and please read it, and whenever you see here the Meta agent search, this is not the company Meta, but this is just the how to call this, the superior, the above certain levels here search. And the beauty here is a representation that can express linear sequences, conditional logic, loops, and it incorporates here the graph structures and or the neural network structures. So offering here the most precise control over the workflow execution. So you see, whenever you code here edges in the structure of pure code elements, you can have graph structures, neural network structure, pure code structure in the edges. So those edges here are really a powerful representation of the interplay. Now, we just had a look here at the workflow representation of node and edges, and we look now at edges. Now, next step is we can also, the authors also introduced operators. And you might think, my goodness, is this mathematics? No, not at all. It is simple. They just take here a combination of nodes and they say, hey, if we combine node 1, 4, and 6 in a particular way, we call it kind of a module. We call it kind of a operating shell here. We call it an operator. Nothing else than redefined node combination functions. That's all there is. And if we have this, now you know what's going to happen. We now need a search algorithm because we have a huge search space here with huge workflow possibilities, permutation and whatever. So we need now a Monte Carlo Tree Search algorithm for the automated workflow optimization itself. And of course, this Monte Carlo Tree Search leverages here the tree structured experience and the execution feedback. This is all there is. 1, 2, 3, 4 elements. If we know those, we can solve this. Of course, it is an optimization problem. What else in AI? So what we have? We have give me a human task, the query, and an evolution function that we can evaluate the performance here. The goal now of the complete workflow optimization here in AFLOW is to discover here a particular solution, a particular workflow W that maximizes here the evaluation function that depends here on the specific multitude of workflows and the user query, the user task. This is it. This is the core concept that is behind all of this. Now, this particular structure that we have chosen transforms now the workflow into a vast search space. Remember when we did the embedding here of semantic objects into a vector space with sentence BERT? Now we do transform the complete agentic workflow in a vast search space, in a mathematical space, encompassing here a wide variety and combination and variation and pluralification of potential configurations. So, key model, key idea, model the workflow as a sequence of interconnected LLM invocating nodes, build an operator structure above it, where each node represents an action by the LLM. You know this, retrieve information, start a logical deduction, whatever, do an output. And the edges define now the logic, the dependencies, and the flow between these actions of the LLMs. The beauty is, if we represent the workflow as flexible nodes connected now by code-based edges, we can code everything. No? Workflow is now represented as a code object, as a code structure, allowing us for a flexible, precise definition of the sequence, condition loops, and everything in between. So here we have it now. Beautiful. So what we have a huge, vast mathematical space, the search space, with a lot of different possibilities of alteration, modification, extensions, whatever to the code. And now we use here simply the Monte Carlo Tree Search mechanism to solve here the optimization problem, find the best workflow for the user query. So what we do? 4 easy steps. Soft mixed probability selection. We have a balanced exploration and exploitation phase, as you know from Monte Carlo Tree Search, by combining uniform random selection with score-based selection. And this simply has a function that it helps us avoid getting stuck in a local minima, optima, whatever. Second, now we use the intelligence of the LLMs. So the power and the intelligence, quotation mark, of the LLMs are now crucial, essential, that we can now expand here the node in the search tree by proposing now specific modification to the workflow code. Everything we do now with the workflow depends only on the cleverness, intelligence, pre-training data of our LLMs. Third step, if we have now a new modified workflow, we execute this workflow and we evaluate its performance. It's a trial and error. We try it out, we evaluate it, now we know it's good, better, or we just delete it. And then we have Monte Carlo Tree Search, backpropagation. The results of the evaluations are propagated back up the tree to inform future search decisions. It is simple if you just break it down here into this understanding. And therefore now, if I look at this beautiful, I think it was here the very first information I gave you in this video, now you understand what's happening here on the left side. Because now you understand that the AFLOW algorithm now has simply 6 steps. We start with an initialization of the system. So we have a template workflow and we split simply the dataset into a validation dataset and a test dataset, as always. Then we have the selection phase. Uses here soft mix probability selection to choose which workflow to expand next. So remember, LLMs generate here these new workflows by modifying the code of the selected workflows. And then, in order to find out, hey, does it improve our system? We have the evaluation. So executes the workflow and evaluates their performance on validation data. Then we know exactly where we are here with this particular modified code in our workflow. Then Monte Carlo Tree Search, we have backpropagation. Updates the search tree with the performance results to inform future selections. And then, if we have run through this multiple times, the process continues until a convergence criteria is now met, or if you have a maximum number of iteration is reached. This is all that is now noted here in this kind of algorithm. One detailed explanation of the AFLOW algorithm. So you see, it is easy. Take your time whenever. I encountered this, and honestly, just looking at this here on the left side, I got nothing. I did not even understand what it was all about. And you see, simple steps, 10 minutes later, we understand it. What is the benchmark telling us? This new methodology, AFLOW, was tested on 6 benchmark data, yes. And it showed almost 20% improvement over existing automated approaches. So given the area here of automated approaches, this looks now as the alpha candidate. Beautiful. But also they tell us here over state-of-the-art baselines that includes human-crafted workflows. It showed here only on this 6 tests, benchmark data, it showed a 5.7% average improvement over state-of-the-art baselines. Interesting, no? So, and the authors here particular mention this here. So let me give you here also this perspective, which I find a little bit interesting. They say, this reduces here the human effort. And I understand this if you are a global corporation and you want to increase the shareholder value of your global corporation. You say, hey, all those humans, this extreme cost that we have with human coders, with human software engineering, with human specialists, with human engineers, you get the idea. And then the open source community here at the universities and research centers and wherever, they are so willing to generate new, brilliant ideas about automation like this here. This new methodology automates here the process of creating complex agentic AI workflows. Beautiful. Saving human time, saving human resources, and saving human costs for global corporations. So great. So if we have now a complete automation for agentic AI workflows, for agentic system, for multi-agent, whatever, not necessarily requiring any human intervention, not necessarily requiring any human resources to be in the loop, and therefore having eliminated all human costs for this global corporation. This is a fact I have to say I'm interested because, I never watched here the carefully designed planning for the elimination of a complete. But we are doing it. This is interesting. So there you have it. Now we went here from a more or less abstract explanation here of an AFLOW algorithm to my personal, yes, and I do have emotions, AFLOW explanation. What is going on? What is the main idea of this? And it would be great to see you in my next video.